Okay, exam 4, fall 2018. First answer is A. How many revolutions is 400 degrees? Well, look, 400 degrees, I know that one revolution equals 360 degrees. And so 400 is just a little bit over 1. So let's just get rid of all those and say that it's 1.1. But if I really want to go through the calculation, I say 400 degrees, 360, one revolution. That's equal to 1.1. What is the angular displacement of a clock's hour hand? There's our clock. There's noon. There's 6 p.m. So the hour hand starts there and it goes through there. That angle is 180 degrees, which is equal to pi radians. See, a car rounds a curve on a flat road. The coefficient there is mu. Curve has a radius of 50 meters. What is the maximum safe speed? So I know that the centripetal force is equal to my static frictional force. That's mv squared over r is equal to mu mg. My m's cancel out, which is good because I don't have the mass. Turns out the speed is not dependent upon m. And so v is equal to square of mu gr. That's the square root of 0.710, and the radius, which was 50, that's equal to 19 meters per second. Yeah, 18.7 or 19 meters per second. Ferris wheel, the radius of 20 meters, rotates at a speed of 1 revolution per minute. Person with a mass of 100 kilograms sits in a chair. The person is at the lowest point. What is the normal force acting on the person? So here's my Ferris wheel. The forces that I have are a normal force and a weight. And so I know that the sum of the forces, Fn minus Fw, is equal to mv squared over r. That's just Newton's second law, right? The sum of the forces equals ma. And we need to recognize that my acceleration is in that direction, my centripetal acceleration. So this is a positive value. If the person was at the top, I would know that the the um, the acceleration will be downward because acceleration is always center seeking centripetal acceleration. So I solve this for Fn, that's Fw plus mv squared over r. So I know that oh goodness, I've lost some of my stuff. Get rid of this right here. I know that my my normal force is going to be a little bit bigger than the weight, so I can get rid of this answer. I can also get rid of B because my weight is equal to 1,000 newtons. 100 kilograms times G is 1,000 plus 100 kilograms times V. Oh, look, I don't have V, so I can do two things. I can either say I can get rid of this and say m omega squared r. That's my alternative expression for centripetal force. Or I could calculate V, which is equal to omega times r. I'm going to take the former option. So I have m times omega. It needs to be in radians per second, so 0.1 squared times my radius, which is 20. So that's 1,000 plus 20. 1,000 plus 20. So it should be A is the answer. It's just a little bit more than the weight, just 20 extra newtons. We could probably say, I'm not going to feel a force that's 3 times my weight in this Ferris wheel that is going around, at a modest pace at 1 revolution per minute. And I could probably it's a little less obvious, but I could probably also say I'm not going to feel an extra 200 newtons of force. If you've ever been in a Ferris wheel, you got to be going pretty darn fast to feel a force that big. So the answer is 1,020. Fan spins at 12 revolutions per second. You turn it off and it slows at 3 revolutions per second squared. What is the angular displacement for coming to rest? This was a tutor question. So I have omega naught there. This is my alpha. This is my omega final. And I need to know what is theta. I know that theta is equal to omega naught times t plus 1/2 alpha t squared. But look, I don't know t, so I need to do something to find t. I use this omega equals omega naught plus alpha t, and here I do know everything but t. So I have omega is equal to 0, that's my final, 12 revolutions per second, plus alpha. It is slowing, so that means alpha is opposite omega, so that's negative 3 revolutions per second squared times t. So t is equal to 4 seconds. And then I take that 4 seconds over here, and I have 12 times 4 plus 1/2 of negative 3 times 4 squared. That's 48 minus 8 is 24. So A is number 6. Equals 24 revolutions. Notice I didn't have to change the units on these. I didn't have to change the radians, that my units all come out in the end. Consider 2 pits on a CD, one close to the center and one close to the outer edge. When the CD makes one full rotation, which pit would have gone through a greater angle of rotation? Which one would have covered a greater arc length? Okay, so this comes back to our what is the definition of a rigid body? And in a rigid body, every point has the same angular velocity. So the greater angle of rotation would be the same for both pits. So here's my CD. I have a pit here and a pit here. They're going to both, through one full rotation, they're going to both go through, well, one full rotation. So I can get rid of A and B. It's either C or D. And then the one near the outer edge, because theta, or excuse me, S is equal to theta R, the one with the greater radius will experience a greater arc length. So C is right. 7, that was straight from OpenStax. It was verbatim. And number 8 is too, I think. Yeah, number 8 is from your OpenStax. Hoop has a radius of 2 meters and a mass of 10 kilograms. The hoop rolls at a speed of 4 meters per second. What is the total energy of the rolling hoop? So total should key you off here that I'm looking for the translational and the kinetic. So my energy is 1/2 I omega squared plus 1/2 mv squared. Now I have m and v, right? Here's my v, here's my m. So I have that, but I need to figure out what I and omega are. So I'm going to put that off here on the side. If I look on my equation sheet, let me pause while I pull it down. So a hoop has a moment of inertia equal to mr squared. So I will use that. I is equal to mr squared. Notice this is the same equation that we have for discrete particles, right? But they're two different things. One's a hoop and one's are discrete particles. They're sort of similar. You can think of a hoop as just a whole bunch of discrete particles all at the same radius. So I have m times 2 squared, 10 times 2 squared. That's equal to 40 kilogram meter squared. And then I also need to find what is omega. But I know that omega, well, V is omega R, so omega is V divided by R. So it's going to be 4 divided by 2, or 2 radians per second. So now I have my values. I have 1/2 of I, which is 40, omega, which is 2 squared, plus 1/2 of 10 times V, which is 4 squared. So that's 20 times 4, that's 80, plus 5 times 16, that's also 80. So the total energy is 160. Figure skater pulls her arms in to decrease her moment of inertia by a factor of 2. As a result, she spins twice as fast. What has happened to her rotational energy? This isn't straight from OpenStax, but it's very similar to one. So L is equal to I omega. If she decreases her moment of inertia by a factor of 2, that means omega increases by a factor of 2. And now let's look at our kinetic energy, 1/2 I omega squared. I'm increasing this by a factor of 2 and having this, which gives me a net increase of twice the total kinetic energy. So B is going to be number 9. Okay, you're supposed to rank these from least to greatest moment of inertia. But the first thing is just recognize that B and C are identical, that they're just rotated on the side. So I'm looking for one that has B is equal to C. And then also need to recognize that because I have this axis all along an arm of this object, that means that the moment of inertia of that arm, that piece, is null. That it contributes nothing to the moment of inertia because r is equal to 0. Whereas that's not true for A or D. So B and C are also the smallest ones. So I can get rid of A as well. So now it's really just a matter of which is bigger, A or D. Well, A has a whole lot of mass out at the biggest radius possible, and it has very little mass in close to the axis. Whereas if you notice D here, it has quite a lot of mass at it very close to the axis. So A is going to have the biggest moments of inertia. D will be the next smallest, and then B and C are the smallest, and they're equal to one another. So B is 10. Merry-go-round has a moment of inertia of 200 kilogram meters squared and a radius of 1 meter, and then a 50 kilogram kid jumps on. What is the moment of inertia of the system now? So initially my merry-go-round just has a moment of inertia of 200. But then I add this extra bit. I put this kid on the edge. He's at a radius equal to 1 meter, and he has a mass of 50 kilograms. And so that's going to be mr squared, or 50 kilograms, times 1 meter squared. That's 250 kilogram meters squared. So 11 is A. Buckets are spinning horizontally. I think this was OpenStax. No, well, maybe it was. Anyway, which of these statements is true as rain falls into them? Well, as I get more and more water into the buckets, their mass will increase, and that means that their moment of inertia will increase. And since L is equal to I times omega, I goes up, that means omega goes down. So this will remain constant. That gets rid of C. The bucket's angular speed will decrease. Yep, B is the right answer. Object is a moment of inertia of 10 and it's rotating at 6 revolutions per second, and then it gets bigger. It's like a figure skater opening out her arms. It increases. It goes from 10 to 20, so it increases by a factor of 2. So you could probably just say right off, well, if the I is increasing by a factor of 2, then omega has to decrease by a factor of 2, and you'd say that C is the right answer, and then you can move on. But let's take our conservation of momentum. Li is equal to Lf. 10, oops, sorry. I initial omega initial equals I final omega final. I initial is 10 times 6 equals to 20 times omega final, and then that gives us omega final is equal to 3. Use a class 1 lever. This is a class 1 lever that where the axis of rotation, or the fulcrum, is in between the effort force and the resistance force. You didn't need to know that, but I lift an object of 12 kilograms. The distance from the axis of rotation to the object is 3 meters, and this distance is 1 meter. And I have a force of 120 newtons over here. What minimum force must be applied here in order to lift this object? Well, you could probably look at if you're clever with this yet, you can just look at the proportions of the moment arms and know that this force must be 360 newtons, 3 times the force. But I'll balance the torques. We'll call that one on the left torque 1 and the one on the right torque 2. And I would say force times 1 meter, that's the length of the moment arm, is equal to 120 newtons times 3 meters. And then you would find that force is 360 newtons. A force is applied 3 meters away from the pivot point, and it produces a torque. How much force would have to be applied to produce the same amount of torque if it were applied 1 meter from the pivot point? Hey, look, this is the same question, so E is the right answer. I have a force applied 3 meters from the axis of rotation, and then I apply another force 1 meter. How much must this force be? It has to be 3 times the initial force. What is the net torque here? Well, first of all, it's rotating about this point, so I get rid of that force completely. This is over here, the 25 Newton causes a clockwise torque, so it's a negative torque. I'll call that torque 1. And this one produces a counterclockwise torque, so I'll call this positive torque 2. Recognize that only a component of this force causes a torque, so that's where my torque will equal to F sine 30. That sine 30 is in our equation for torques, but it comes about from, I'm just taking the y component of the force. So the net torque will be negative torque 1 plus torque 2. That's negative 25 times 2 plus 10 times 2 meters times sine of 30. Sine of 30 is a half, so that's negative 50. Oops. Negative 50 plus 10 is equal to negative 40. The negative says it's clockwise, so A is the right answer. And then after 3 seconds, what is the angular speed of the bar? So several steps you have to do. First, we need to find I. And for a bar, the moment of inertia is 1/12 mv squared. So 1/12 of the mass was the mass. 3 kilograms times the length squared, that's 4 meters. So 3 kilograms, 4 meters squared, uh, is 4 kilogram meters squared. That's I. Then we need to find what is alpha. Alpha is torque over I. So our torque was negative 40 over 4. That's equal to negative 10 radians per second squared. The negative is not really important. That just means that it's going in a clockwise direction. And here, after 3 seconds, I want to know what is the angular speed. Omega naught is 0 because it's initially at rest. And so it's going to be negative 10 times 3 seconds, or negative 30 radians per second. 30 radians per second in a clockwise direction. I was just asking for the speed, so E is the right answer. All right, what is the magnitude of the angular acceleration of the hoop? This was a similar question, a very similar question. So what you need to do is find the moment of inertia for a hoop. We've already seen that. It's mr squared. That's going to be 2 times 1 squared, the mass times the radius squared. So 2 kilogram meters squared. Then we also need to find what is the net torque. There's only one force, 30 newtons, acting at 1 meter. So it's 30 newton meters. And then the acceleration, alpha, is torque over I. That's 30 over 2. So it's 15 radians per second squared. Turns out it's positive 15 because it's counterclockwise. You want to completely submerge a block of ice with mass a half a kilogram in liquid water. What force, not two forces, just what force must you exert on the block in order to do so? All right. This seems like a simple question, but it's not. There are several things, and this was like the grouper question that you had in OpenStax. I have a block of water. There are two forces acting on it, the buoyant force and the weight. All right, the weight is equal to a half times 10 is equal to 5 newtons. I just multiplied this times g. Now the buoyant force is equal to the density of water, liquid water, times the volume of the block times g. I don't know the volume of the block, and that's what makes this a little tricky. To find the volume of the block, I say the density of ice is equal to mass of the block divided by the volume of the block. The density of ice, it's not given here, it is on your equation sheet. The density of ice is 917. And so I have the volume of the block equals the mass of the block over the density of the block. That's a half a kilogram over 917 kilograms per cubic meter. And that'll give me the volume. So it's 5.5 times 10 to the minus 3. That's cubic meters. Then I want to calculate what is the buoyant force. So the density of water is 1,000 kilograms per cubic meter. That's on your equation sheet, but you probably know it. Times 5.5 times 10 to the minus 3 times g, which is 10. That's 55 newtons. Hold on, I have a mistake here. Let me find it. I'm going to pause for just a sec. Okay, I found my mistake. Sorry. This should not be 3. This is -4. That would be a really big buoyant force. 55 newtons on this little block of ice. That means you'd have to exert like 50 newtons. So anyway, this should be a -4. It's just a calculation error. And so this is 5.5 newtons. Isn't that right? Yeah, 5.5 newtons. And so that means that I have an additional force of 5.5 newtons that's buoying this thing up, which means that in order to hold it submerged, I have to take the difference between these two, 5.5 minus 5, which is going to be, I think I rounded a little bit differently. The answer here is B, number 19, but I'll change it so that it's 0.5. That keeps proper sig figs, I think. Yeah, that keeps proper sig figs. I'll revisit that. So that's number 19. All right, sorry about that. Block of unknown density is floating in a fluid, such as in this figure. Uh, which of these statements about the density is true? The block is less dense. That's why it's floating. Water flows through a pipe. The pressure is 2,000. I'm going to call this P1. It flows at 1 meter per second. That's V1. And this is V2. I want to know what is the pressure in this second pipe. So this is what we have, a pipe like this. Gets smaller. I have a pressure here and a V1 here. And I have a pressure here, P2, and a V2 here. Now I know that V2 is increased. That's why I was able to draw the pipe like this, because it gets narrower, and by the equation of continuity, the velocity has to go up. Um, I also know that when the velocity goes up, that the pressure must decrease. So I know right off that PT must be less than P1. And since P1 is 2,000, oh shoot, well, I can go ahead and tell you the answer is C right away. But let's go ahead and work it out. So P1, the Bernoulli equation says that P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. And so P1 is 2,000 plus 1/2 of 1,000, that's the density of water, times V1 squared is equal to P2, that's what I want to know, plus 1/2 of rho, which is 1,000, times V2, which is 2 squared. So this is 500, 2,500 equals P2 plus 2,000. And so P2 is equal to 500 as we expected. Swift wind blows across the top of a chimney. What happens to the smoke rising inside of the chimney? As V goes up, pressure goes down. That's Bernoulli's principle. So that means that in this chimney, here's my smoke, I'll have this strong wind. I will have a pressure that is lower, which means that this stuff will come up. So the smoke rises more quickly. Which fills a larger volume, 100 kilograms of gold or 100 kilograms of lead? Well, let's look at their densities. Gold is 19.3, lead is 10.5. So gold is more dense, it means it takes up less volume for the same mass. So that means the lead fills a larger volume. This shows a hydraulic lift. I want to know what is the weight of the truck, or the car in this case. And so I know that the pressure 1 is equal to pressure 2. That's Pascal's principle. F1 over A1 equals F2 over A2. F1 is given. I think this was directly from OpenStax. 100 over 0.01 equals F2 over 8 over 1. And 100 over 0.01 is 1,000 is 10,000 newtons. So 24 is B. Okay, cylindrical container is 4 meters tall and has a diameter of 2 meters. So 4 meters. This is 2 meters. Notice that's the diameter, so the radius is 1. The container is not full, so I have some liquid inside of the pressure, inside of it, and it contains 200 kilograms of water. and I want to know what is the pressure exerted on the bottom of the container by the wall, by the water, excuse me. So pressure is force over area. I think you had a tutor question like this. Yeah, this was from tutor. So my force is the weight of the fluid, 200 times 10, that's G, M times G, divided by the area, which is going to be pi times the radius, which is 1 meter squared. So it's 2,000 divided by pi, which is 637, 640 pascals is 25. Which statement best describes the relationship between P and P naught? Well, P is less than P naught, right? P naught is pushing down on this side and pushing up that column. It's less, and it's less by the amount rho GH. Which of these is compressible? Solids are not compressible, liquids are not compressible, only gases. So C is. And who's awesome? The guy next to me, the lady in front of me, the fellow on my right. All of you are awesome. All right, that's all.